Hello. Today we will be doing a presentation on the statistical learning theory project. When we had to choose two papers that we want to present about, and the two papers that we have chosen today are the tree of thoughts, deliberate problem solving with large language models, and the second is the self-rag, learning to retrieve, generate, and critique through self-reflection. Now, starting off with tree of thoughts. Recent large language models are actually very capable in a variety of tasks, ranging from mathematical, symbolic, common sense, and knowledge reasoning. However, it is true that these large language models still run the original autoregressive mechanism where the next token is predicted on a one by one basis from left to right, where left to right. For example, the next word will be predicted from the previous words that has been generated from the large language model. From this, it raises a question whether or not this autoregressive mechanism is sufficient enough to become a general problem solver that we want the LLMs to be. Now, let us backtrack a bit from the LLMs and let us borrow intuition from the human decision-making process. It is known that the human decision-making process is primarily composed of two systems, where the first system, System 1, is fast and automatic and happens in our unconscious minds, and the second, System 2, is slow and deliberate but happens on our conscious mind. The current simple token level choices of LLMs are pretty much reminiscent of the fast and automatic System 1. And from here, then, if an architecture that corresponds to System 2 of the human decision-making process is applied to an LLM, we believe that we can hypothesize that the overall performance of the decision-making process of the LLM would increase. Now, from this, from this hypothesis the tree of thoughts has come out. And tree of thought is basically a framework for language model inference that enables exploration over the coherent unit of text, or also known as the thoughts, where each node here represents a thought, that serve as intermediate steps towards problem solving. Now, before we go on to the actual part of explaining the tree of thoughts, let us go over the related works. The first related works is the input-output prompting, where it is the most common way to turn a problem where it is input with X into output Y with an LLM. The prompt can wrap the input X with instructions and sometimes even with examples of the correct way to answer the question. Going on to the next one, this is more advanced version of I/O, where it is called the chain of thoughts. This is actually where the tree of thoughts has branched off from. It is proposed to address non-trivial cases where the input X to output Y are mapped, where the X may be a math question and the Y may be a numerical answer to the math question. And it introduces a concept called the chain of thoughts to bridge the gap between X and Y, where each thought is represented via Zi, where I is the number of intermediate thoughts available between the input and output, and each thought is sampled sequentially and followed by an output. And the overall sequence of the output is sampled as a continuous language sequence, and how the sequence is decomposed is still left ambiguous, which is a property that we do not want in the tree of thoughts. Now, improving upon the chain of thoughts, self-consistency with chain of thoughts was introduced. The baseline is the same, but it introduces a new sample method where K IID chains of thoughts are sampled from the most frequent output. And it can therefore be said to explore the more richer set of thoughts or nodes, improving upon the COT's performance. But as same with COT, this isn't really decision making, and there's no local exploration of different thought steps, and just does everything probabilistically. Now, let us move over to the method part of the tree of thoughts. Recent research on human problem solving suggests that people search through this problem space tree, where the TOT tries to mimic this by using a tree structure, framing any problem as a search over a tree. We can see that each node on the right, we can see a more detailed look at this tree of thoughts, and where each node is a state, and each node is a partial solution of the input and previous nodes. For example, if you're solving a math question, then each node would be a single step into solving the math question. A specific instantation of this tree of thought is composed of four major questions, which are to be discussed in detail. The first one is thought decomposition, where the tree of thoughts initially uses the problem properties to design and decompose the intermediate thought steps, denoted Z1 to Zi. For example, for a crossword problem, a thought could be a couple of words, and for each of these thoughts, a thought should be small enough so that the LMs can generate promising but diverse samples, but also big enough so that the model is able to evaluate the prospect towards the problem solving. For the thought generator, we are given tree states denoted S, wherein two strategies that can be considered to generate the next thought from the previous thought. The two ways are: the first one is sampling, where it samples IID thoughts from a COT prompt and this works ideally when thought space is rich, leading to diversity. And the second is a proposed sequential thoughts, where it uses a proposed prompt to propose thoughts sequentially. Contrary to sampling, this works best when the thought space is constrained. Different thought proposals are from the same thought prevent duplication of thoughts. And after all these are processed, we finally reach the search algorithm, where different search algorithms can be used for the tree of thoughts. For the paper, two methods were explored, where the breadth first search the first is the breadth first search, where it maintains a set of B at most promising states per step. The second is the depth first search, where it explores the promising states until the final output is reached, or else the evaluator just deems it impossible to solve the problem from the current state. And let us go over the experiments and the results of the TOT. The authors of this paper introduced three new tasks, where even GPT-4 finds it difficult to answer. And the first is game of 24. The second is creative writing. The third is 5x5 crosswords. The exact configurations, please refer to the paper due to time constraints. The game of 24 is a mathematical reasoning challenge where the goal is to use the provided four numbers and basic arithmetic operations to obtain 24, where the example is given below. 5 in-context examples were provided initially for the LLM to know how to answer the question. It can be seen from the results that three related works all perform very poorly on this task, and TOT variants show a much higher success rate of 45%, 74%. And we can see that from the middle that the success rate of the TOT is the best. And also on the right, we can see that the TOT failed the least for each thought step, resulting in much less failures during the thought steps. Creative writing is a task where 4 random sentences are input, and output should be a coherent passage with 4 paragraphs, where each paragraph should end in the 4 input sentences respectively. This task is open-ended, requires a high-level planning from the LLM, and 2 evaluators were used, where the first is the GPT-4 zero shot and the second is human scoring. The crossword task is an evaluation task designed to exploit the TOT architecture, unlike the other two. The goal is not to solve this task, but serve more as a general crossword that can be readily solved with specialized NLP pipelines. The aim of this is to explore the limit of the LM as a general problem solver, and where it is provided with 5 examples of input outputs. It can be seen that the IO and COT methods perform poorly, especially in the explaining the word success rate, and it can be seen that the TOT outperforms the counterparts by almost double the score and in letter and quadruple in word. Now, these are the two most ways that this paper has contributed. The first is to propose a framework that uses off-the-shelf LLMs to autonomously and intelligently make decisions to solve decision-making problems. And the second is to improve interpretability of models, decisions, and opportunities for human alignment compared to current LLMs which are behind the curtain. Now, this tree of thoughts isn't without its limits, and this deliberate search method, it might not be necessary for many existing tasks, like the current LLMs, such as GPT-4, is already able to answer pretty well. This paper explores 3 tasks that GPT-4 deems as challenging, but it might not be in the real-world scenarios, and there might be more complex scenarios that we need to validate this on. And also, due to using the LLMs just as thoughts, this requires more resources, which is a problem. And also the fine-tuning of current LLMs using this TOT style counterfactual decision making actually might present opportunities to enhance problem-solving capabilities of LLMs without using the tree of thought framework.
Hello, my name is Guanyoung Koo, and now I'll be presenting about self-lag, learning to retrieve, generate, and critique through self-reflection. This paper is already accepted to iShader 2024 conference, so let's move on to introduction. Before introducing this paper, I'll briefly talk about how to integrate external data with large language models. When it comes to injecting knowledge that was not included during the training phase of the LLM, there are 2 main methods. The first one is fine-tuning. This involves fine-tuning the LLM's parameters using text data related to the new knowledge. Essentially, we can update the model to better understand and incorporate the new information. And the second method is retrieval augmented generation, in short lag. This method involves embedding external data sources and storing them in a vector store. The model can retrieve and utilize this knowledge when generating answers, and this allows the model to access up-to-date and relevant information without retrained. And RAG can be applied in various contexts. For instance, it is useful for Q&A chatbot, and by integrating LLMs with chatbots, companies can derive more accurate answers from their documents and knowledge bases, improving the quality of automated customer support. And another application is search augmentation, and RAG can also be used as a knowledge engine for querying data. Then how does self-lag work? The self-lag introduced some innovative concepts such as reflection tokens, which were further categorized into retrieval tokens and critique tokens. The process works in several steps. The first, there is self-evaluation for retrieval needs. The model initially assesses whether additional retrieval is necessary to address the user's query. If retrieval is needed, a retrieval token is set to 1, otherwise it remains at 0. And second is generation and evaluation of retrieval passages. Here, the model generates and evaluates the retrieval passage. Then this model produces the task output based on this evaluation. And finally, there is a self-assessment with a critique token. This step ensures quality where the model generates a critique token for self-assessments. And self-lag offers advantages over conventional lag. While conventional lag uses fixed retrieval method, for example top K retrieval, the self-lag performs retrieval as needed, providing much greater flexibility. Moreover, self-lag offers self-assessment and citations, which enable ease-effect verification and enhance the reliability of the output. And let's move on to related works. The conventional previous lag has some limitations. One major issue is runtime inefficiency, which can lead to increased latency due to frequent retrieval processes. This makes the system slower and less efficient. And another issue is reduced robustness. Conventional lag always performs top K searches, even when retrieval is unnecessary, leading to inefficiencies. And lastly, there is a lack of explainability. The conventional lag lacks the ability to explain what references the output was based on, and making it unclear which sources were used. Let's move on to method. This is the overview of self-lag, and the left part of this figure refers to traditional lag. This traditional lag involves searching from a fixed number of documents and concatenating the search results with the prompt before inputting it into a language model. This can cause issues like contradictory information and lack of relevant information. And for self-lag, as you can see, the right part of this figure retrieves only as much information as needed and generates outputs in parallel for each document retrieved. The language model itself decides the relevance of each document and the support it provides to the generated output. Then through critic tokens and reflection tokens, the model can assess the quality of its output, and it can select the best output and retrieve it further if necessary. And if retrieval is not needed, the model operates without it, and similar to traditional language model. So this is the overview of self-lag, and I'll go over this part. So in self-lag, two types of tokens play crucial role. The first token is retrieval token. This token decides whether additional information is needed when input X is received. And the second token is critic token, and there are three types of critic tokens. The first is relevant. It determines if the retrieved information is necessary to address input X, and is support token assess if the generated output Y is derived from the document, and is useful token evaluate if the output Y generated from input X is useful. And here is a training overview. Retrieve tokens train the generator M to use reflection tokens as part of the language model's vocabulary. And the critic model, in short, we called it C, and this critic model plays an essential role. It predicts reflection tokens for evaluating retrieved passages and output quality. And reflection tokens are inserted into a training corpus and preparing the language model for inference without the critic model. So the first phase of training is data collection. The role of critic model is crucial for generating reflection tokens, which guide the generator model M during the self-lag process. So for data collection, GPT-4 is used for generating initial reflection tokens, and this approach mitigates dependency on proprietary language models to avoid API cost and ensures reproducibility. And typically 4K and 20K dataset data instances are collected for each types of reflection tokens. And for the second phase is learning. So the critic model is initialized with a pre-trained language model such as Llama 2.7 billion model, and it is trained to maximize the likelihood of a correct reflection token prediction. So it achieves over 90% agreement with GPT-4 predictions across most categories. So objective functions are as shown in here. And during inference, reflection tokens for control of inference allow self-lag to self-evaluate and control output during the process, and tailoring its behavior to task requirements and balancing factual accuracy and creativity. And customizing inference behavior involves scoring a segment based on the critic token's probabilities. And the hyperparameter allows for weighting different critic aspects, and hard constraints can be enforced by filtering out segments with undesirable critic tokens. So let's move on to experiments. I'll briefly discuss the experiments. The primary goal of this experiment is to evaluate the performance of self-lag against various baseline models across multiple tasks. So for metric, so to evaluate the model, This paper used three key metrics: overall correctness, factuality, and fluency. And for dataset, this paper utilized several datasets for specific types of tasks. So for short form generation task, PubQA and Trivia QA unfiltered dataset are used, and for closed set task, the fact verification dataset and multiple choice reasoning dataset are used, and lastly, long form generation task, biograph generation, and ASQA long form QA task dataset are used. And in these experiments, SelfLeg evaluates several baseline models without the use of retrievers to understand the inherent capabilities of different model and configurations. So there are various baseline without retrievers. So here are results. SelfLeg show superior performance across all tasks, and it outperforms ChatGPT in PubHealth and PubQA biography generation and ASQA dataset. And SelfLeg excels the standard among non-priority models on all tasks, and it outperforms instruction-tuned model with retriever in most cases. And from the results, we can see that the SelfLeg's advantage in citation metric. SelfLeg achieves higher citation precision and record than other methods except ChatGPT in ASQA, and also it demonstrates the ability to generate well-supported claims with cited evidence. And also, the impact of model size is very interesting. The SelfReg 7 billion model occasionally outperforms 13 billion, suggesting smaller models generate more precise and concise outputs. And here are some limitations in this paper. The baseline with retriever show limited improvement in tasks that require more than simply copying or extracting from retrieved passages. And also, SelfLeg struggle to improve citation accuracy in long-form generation tasks like ASQA. And thank you for listening.